Hello and a warm welcome to the next project. In this set of videos, we will be dealing with the ventilation flow in an indoor environment. We will be trying to replicate one of the experimental study in a closed environment, and the application of this particular project can be associated with any indoor environments. Like you may try to follow the same strategy and also the validation procedure for any indoor environment that you can consider. It can be an aircraft cabin, it can be an hospital room, it can be a hospital room, or it can be a simple home or any office environment. The strategy for setting up the numerical scheme can be applied in any indoor environment. The strategy what you're going to learn right now. And in order to work on this particular thing, I have an experimental investigation which I have extracted the data. And if you want, you can just try to Google and try to download the relevant publication that is this topic. Okay, and it is published in this particular journal. Now I will not be showing you the complete PDF. If you are really interested, you can just download it from the respected website, but I have extracted the significant information which is quite necessary for us to replicate the same aspects. Now one more thing over here to mention, we are trying to simulate this thing in a academic version or in an academic version of ANSYS. The domain is three-dimensional over here. I'm not sure whether the elements or the mesh what we are going to create in this domain will suffice for the academic version. Nevertheless, we can try to simulate and see the differences between the experimental and the numerical results. Now you have this cube-like room over here. They have basically created an experimental setup, right? The dimensions are displayed over here. The length of the model or the length of the room is 0.8 meter. So this is a very scaled room, you can say, and this is quite suitable for the academic version which we are dealing with because of the limitation in the cells, number of cells, or the number of mesh elements what we can create. The height of the room was 0.4 meter and the width of the room is 0.4 meter again. You have an inlet located at some position over here, and you have the outlet which is located at this end. The inlet is supplying a cool air at a velocity of 0.225 meters per second. The air is entering into the room and the air is exhausting from the outlet. So this is a kind of interior environment what we have. The room doesn't have any occupants over here. I mean, the room is empty. They have just visualized the flow field and the air movement in the room. Now the next thing what they have investigated over here is at this particular point, that is x is equal to 0.2 meter, x is equal to 0.4 meter, and x is equal to 0.6 meter. They have they have extracted the values of velocity at these three positions along the y or along the z direction, that is along the height of the room. Now what we are going to do is we will be creating the model or the geometry as it is. We will divide the domain into small elements, that is we will be discretizing it by creating a mesh or a grid, and after that we will be considering a numerical scheme for these kind of cases. Okay, and we will be applying that particular setup, and we will be simulating the results, simulating the model, and from the results we will be comparing the x velocity on these three positions and see the differences between numerical and experimental study. In the next slide you can see the pattern which was mentioned in the respected publication. So they have extracted the flow field and they have represented. So the flow field obtained through CFD shall be closer to this respected given data. Not only that, as I mentioned you that they have investigated the velocity in the z direction for at three positions, that is x equal 0.2, x equal 0.4 and x equals 0.6 meters. And even they have simulated it. You can see the curve what they have obtained in their simulation. And generally the experimental results will be mentioned with the help of dots, because experimental cases are not along this complete line, they are measured at intervals or certain gaps. That is the reason you'll be having a gap between each data of the experimental result. Now more or less you can see the pattern of simulation and experimental is exactly similar for their case. We shall also try to set up the scheme in a way that gives us an appropriate result or similar result with the by comparing it with the experimental data. So after the simulation is completed, we will be extracting the x velocity values at three positions along the z direction, and then we will be comparing the experimental and our present CFD results. So this is what is in this workshop, in this project. Let us see how and what we are what strategy are we following to create and solve this problem. Let us move to the next video.